Okay. So here we've got a man holding and I'm just going to draw this kind of sticky, but it's the best way I can do. So this is an arm holding a ball. Okay, and the ball weighs 178 newtons. And that should be straight down. Any deviation from straight down is just my lack of drawing ability. The center of gravity of the arm is about here, and the arm weighs 22 newtons. The muscle in the arm pulls up about here and is labeled M. And then the arm bone would also apply a normal force. The distance is in here, so the distance from the pivot of the arm to M is given as 0.0510 meters. The distance from the muscle to the center of gravity of the arm is given as 0.0890 meters. And the distance from the pivot to the center of gravity of the ball is 0.330 meters. And so we're looking for two things. The value of M and the value of N that I've shown in this figure. So to solve for the value of M, we're going to use that, well, the arm is stationary, so everything is stationary. So to solve for the value of M, we're going to use that nothing's rotating around this rotation point. And so everything's going to be related from there. And so what I mean by that is that the sum of our torque, which is equal to I alpha, is 0. So the sum of our torques is equal to 0. And now we can go through and figure out all our torques. So for our N here, so R equals 0, or torque is equal to F cross R. Right? And in this case, our R is 0, and we can write this also as FR sine theta, where theta is the angle between F and R. But R is 0, so then, and I'm just going to label this a bit better. So for our N force, this equals 0. So for the normal from the elbow joint is 0. For our M force, our torque is F cross R, which in this case is M R sine theta, where I'm using M for the force. Now we need to use the right-hand rule to determine directionality here, just so that we know which one should be negative and which one should be positive. So remember, the right-hand rule is you put your fingers, or at least the right-hand rule that I use, you put your fingers in the direction of the first one, so in this case the force, and then you put your palm in the direction of, so I'm just going to redraw the M force, and you stack them tail to tail, so there's the R, and so you put your right hand fingers in the direction of the force, and then your palm should be in the direction of the R, and then your thumb points in the direction of the torque. So in this case, our torque is into the page, and I'm going to go ahead and define that as a negative torque. So I'm just going to augment this and say that this is minus mr sine theta. Our theta here is 90 degrees, sine of 90 degrees is 1, and so I'm actually just going to get rid of that too. So then it's just minus mr. Okay, so for our center of gravity here, so I'm just going to call this our mg force. So torque is F cross R, which is equal to 22 newtons is the force, and the R is, actually I'm going to plug this in here too. So the R that we were given for our M is 0.0510 meters. And so this distance here is, I'm actually just going to draw it down here just for space, 0.0510 meters plus 0.0890 meters, which is 22 newtons, times 0.1400 meters. Okay, and again, if we apply the right-hand rule here, the force is going downward, the radius is outward. So then our force is coming out of the page, and I'm defining that positively. So this guy's a positive torque, whereas for M it's a negative torque. And then for the ball, we have very similar. Our torque is F cross R. In this case, our F is the 178 newtons, and our R is the 0.33. If we look at the direction, it's the same as for our mg force, so it's going to be positive. And so this is just going to be 178 newtons times the 0.330 meters. Okay, so now we have our torques. So now our sum of our torques is 0. And so our sum of our torques, if we write out all our torques here, so we have 0 plus, and we don't really need to include the 0, but I'm just doing it for completion. 0 minus m, 0.0510 meters, plus 22 newtons times 0.14, and plus 178 newtons times 0.330 meters. All that equals 0. So now we're in a perfect place to rearrange this for M. And so our M times 0.0510 meters is equal to 12.2 newtons, or our M Newton meters, I should say. And so our M, oh, okay, never mind. I'm just going to erase that, because apparently I did not calculate the intermediate, so our M is 12.2 newtons, which is just 1.2122 times 10 to the 3 newtons. So significantly larger than the other forces. Now to compute our N. To compute our N, we will use not our rotational relationship, but our linear relationship here. So if M is that, so our sum of our forces is equal to MA, which is equal to 0 again, because nothing is moving. So our forces, if we look, and we can easily determine direction, I've got the N acting downward, as well as all the weight forces, and the M acting upwards. So some of our forces then is just minus N plus M minus 22 newtons for the arm mass, and minus 178 newtons for the ball mass. And we actually could have put in the value there, but I'm just going to rearrange and move N to the other side. So N is equal to 1.2122 times 10 to the 3 newtons minus 22 newtons minus 178 newtons. And so then N is 1.012 times 10 to the 3 newtons. And then so there is our normal force from the bone, from the elbow joint. If we check our solution here, we have, given that N is upward, so there's the 1.21 times 10 to the 3, and there's the 1.01. So I would say it's correct, although likely a little harder to follow.